let's just get into actual doing the tutorial. We'll take a little break in the middle of it, and I mean, we kind of did our break already, but take a maybe a 5-minute break in the middle and then continue. Okay, so without further ado, let's get into it. This is our first question that we'll try together here. This I saw in a few final exams, so we'll just do it together and we'll see what's going on. And yes, everything's recorded, and yes, everything's going to be posted, and PDF will be posted, and all these kinds of things. So, okay, given the following circuit, derive its state table and state diagram. If the following sequence is applied to the X input of the circuit with initial state 0, 1, then determine the result output sequence on the Z output. Right, so Z is like an output signal and X is an input signal. Okay, so let's analyze things a little bit here and see what see what we can find here with sometimes there's the complicated pictures and we just want to grab some information. So me looking at this, like I'm immediately like I want to redraw this, right? Because there's a lot of things that like I don't really need to look at. Like the clock signals, I mean all I need to know is that they have the same clock. Okay, great, they have the same clock. So now I don't really need to see these wires. Clears, we're not really going to use the clear for anything. The clear is not connected to anything. It's just an input signal that we could use, but so all that doesn't really matter. VDD, well, sure, but that's I mean, of course, needed electronically, but doesn't affect the logic of the circuit, right? And then there's no need for all these wires to be crisscrossed and everything like this. The general structure of an FSM, and this is an FSM, right? Is as we saw in our labs, is where we have this kind of like clock synchronized component. Then we have like a next state logic, which feeds into that. And then we have an output logic, which feeds back into the next state logic, right? And we might have some inputs here. So this is next state. This is just like clocked logic, and this is our output logic, right? And then the I guess maybe like that is what I mean, right? So we want to put it like in this form. This is a rough picture, but this is kind of the form we want to put an FSM in. So we will do that. So okay, again, like I want to redraw this. So I'll start by erasing things that I don't really care about. And I don't know if you have time for this on the final exam, but it's just at least you can do it in your head, right? So like, we don't care about that. We don't care about that. We don't care about these wires. There is a clock. That's all that matters. We don't care about the clear, right? So I'll just kind of erase things here, right? We don't, not particularly nicely, right? But anyways, we have all this, right? Okay, so that's already, diagram's gotten a lot simpler, right? Let's start redrawing this with a, with our signals. So we have like maybe our Y1 D flip-flop here. These are D flip-flops, right? So that's how we do our kind of register and FSM logic usually, right? And we have some clock that's attached to it. So maybe I'll just label Y1 here. And again, the point of all this is just like we have a cleaner way of thinking about it, right? And that's going to help us with our whole situation here. Yeah, so let's see what's going on, right? So there's a connection like this, okay, which is interesting, right? That's kind of connected up like that, and maybe just for the sake of doing it how I usually do it, is probably best to kind of draw it like this, right? So what I've drawn there is this wire, right? Connects from the output. Oh no, I did it the wrong way, right? Didn't I? So I guess I did it. It connects from the output of Y2. So the output of Y2 connects to the input of Y1, like that. And then, okay, so that's that wire. Then the clock's on the bottom, doesn't really matter. Input of Y2 comes directly from the OR gate here, right? So we have an OR gate like this, and on the OR gate we have X, and the other wire, okay, is from something. Okay, we have to deal with what that is in a second here. But in general, what we're creating is this little bubble here is the like next state logic, right? How we compute the next state for Y1. Well, the next state for Y1 is just whatever Y2 is. And then the next state for Y2 is more complicated, right? So we have to deal with we have to deal with that. So we have a little bit more to put through here. So again, just to kind of color code what I'm doing, right? That's kind of that section. Okay, and then now what's happening, right? We have more wires here, right? So we have our this segment here, which is the other OR gate, right? So the other OR gate comes from the blue segment, right? And it, you know, and computes the well, I guess it compute, yeah, okay, so it comes from the blue segment and into this OR gate, and from Y1 also into that OR gate, right? So what's really happening here is our Z is going to be our output here, right? That's kind of the thing that we need to think about, which is where our output's going to be. The Z is connected to some wire. It's in fact connected to the green wire, right? So we may even want to really, really kind of rearrange this to really put everything in order in how we want it to be. And what I mean by that is this up here. So what I would actually suggest maybe now is to draw this green wire, right? Even though it is partially next state logic because it is here, it's also output logic. And so I might draw the green wire here. And that green wire is the input to Y2 as well. So you see that that kind of comes around to be the next state logic for Y2. But we still have to draw the beginning part, this beginning OR gate. So we have this OR gate. Okay, that's this one. I'm still color coding it on purpose, right? That's that OR gate. And the output of that is, of course, connected here. So I'll just maybe clean it up a little bit, right? The output of that is, of course, connected here. One of the inputs is X. That's all the way over here. So I'll deal with that in a second. The other input, right, is a combination of a few things, right? The other input is, again, another OR gate that connects two things. So maybe I'll start color coding this in a different color, right? That connects two things here, and that's this red segment. That'll be all of this, right? And in that red segment, we will connect one pin to the blue and one pin to the output of Y1. There we go. Okay, and then the very last thing is I need to connect up this X, right? And this X can just be connected like just directly. Like that. It's partially output logic, partially next state logic. But generally, the point of everything I just did is this, right? Is that I've broken it into my three kind of segments. I've broken it into, this is my next state, this is my present state, right? This is my output logic, right? And this is my, input logic. The next state logic is really kind of the same thing, but this is my input / next state logic. This OR gate kind of acts in between an output logic and a next state logic, but that's okay. Okay, so hopefully this, I know that took a second, but the point is mostly just to compare this to what we did in our labs, right? Which was a very similar structure of a circuit, having different components here, these next state logic, generally clocked logic, whatever, usually D flip-flops, some register, and then an output logic. Okay, so now let's run through deriving the state table and state diagram. So the state table, right, is, we have some columns here, right? So we have our current state, right? So we have two columns for whatever our current state is. Sorry, I guess we should be clear here, right? There's two variables, right? It's two state variables. There's two flip-flops, so there's two state variables, right? So we can just call this first one like present state. We can have another column here, which is, it depends, there's a lot of ways to write this, but this is like next state when X is 0. and we can have next state when x is 1. And then we can have like our outputs, right? And so the output depends, this is our output signal right here, right? This output. This output signal is driven by this OR gate. And this OR gate combines present state information with the input variable. So the output depends on the input variable, right? So our output will also be when x is 0 and when x is 1. Right? So our present state variables, we should give them some names. We can give our present state variables, this is like y1, capital Y1, capital Y2. This is like, or I guess, I'm sorry, present, give it lowercase y, I guess, right? This is lowercase y1, lowercase y2, and then capital Y1, capital Y2, right? These are our next state variables. So we are currently in Y2, Y1, and this is Y2, Y1. It's asking a question, when output depends on input, is it a Mealy machine? When the output, yes, right. When the output depends on the input, yeah, that's what it means to be Mealy, right? So that's our Z output depending on the Mealy machine, right? Correct. Now then the other question is, are they XOR gates? Yeah, these are XOR gates, right? These are XOR gates. Like this. Okay, so well, that doesn't, that'll just affect our logic here. Right? So present state, next state, other alternative next state, and then our output is Z, and this is also Z, right? In our different situations. So there's only 4 options, right? So it can be in state 0, state 1, state 2, or state 3. And then we think about what our next state variables are, right? So we have to fill in this table based on this circuit. And again, it's a little bit better if this circuit is drawn like this compared to like this. It's just kind of easier to follow. That's the point of drawing all this, is that it's easier to follow like this. How do we know whether it's Mealy or Moore? So this is like this is the kind of typical question we have from our FSM lab, right? So Mealy machines have an output based on the current state, of course, but also the current input. That's for a Mealy machine. So let's remember that, right? Mealy machines, let's say, okay, next state, output depends on present state, always. Also, input, that makes it a Mealy machine. Okay, so output Z always depends on present state. But if it also depends on input, then it's a Mealy machine. So if we look here, right, our output, right, depends, of course, on the present state, because that's this kind of red, that's the whole red segment. That's why I colored it all one color, right? The whole red segment is the fact that the output Z depends on the present state. But the green, this wire, the specific wire here, maybe not the whole green segment, but just this green segment, right, tells us that the output Z also depends on X, right? Without clocking, if I change X, then the output changes. That's really the key thing. Without affecting the present state. If I change X, if I imagine X is a switch and I flip it up and down, then Z will also change. Because it's this OR gate here. Possibly, right? I mean, if this is fixed at a 1, then of course it won't change, but it could change without clocking. So hopefully that makes sense. Okay. And so let's just try to follow through with what our next state is. So if this is 0, 0, let's just say everything's 0. This is 0, this is 0, X is 0, right? So then, you're just kind of following it through, 0, 0, 0, 0. Z is going to be 0, right? So this is a 0 here. Right? And then our next state, well, that's going to be a 0, and that's also going to be a 0. Right? So that's going to be 2 zeros. One thing to note here, right, is that our Y2, our next state for the second variable, is just Z, right? Is just the same as the output. And the Y1, capital Y1 for the next state, is just lowercase y2. Right? So we can keep that in mind right here, so that y1, our next state variable, y1 is just lowercase y2. So this will be just 0, 1, 1, like that, just matching these columns is what I'm saying. And then again, this column, yeah, I can explain it for sure. This column here will be the same as this output. So again, let's follow through, right? So let's see what is happening with 0, 1, right? So maybe we can, I'll take a screenshot of this picture just so that I can draw on top of it. Right, so this one we'll do kind of in detail. We don't have to do this every time, but let's follow through with what's happening here, right? So let's say, y2, y1 is 0, 1, and x is 0, right? And so we're looking for what's y2, y1, and z, right? Those are the things we're looking for. So just following through here. So this is going to be a 1 and a 0. So immediately, our capital Y1 just always matches Y2. So this is also going to be a 0. So this is equal to 0. And these other two, this capital Y2, is just the same value as Z itself. So once we find these two, right, these two will always be the same value. So Y. So now we just have to find that. So we just trace through with what's happening here, right? So this is a 1 that's being traced through. This is a 0 that's being traced through. 1 XOR 0 is 1. So this 1 is here. And then we need to consider this input for this XOR gate. But the XOR gate is just X itself, right? This is the thing we kind of have control over. And this is a 0. This is also a 1. So that means both of these are 1s. All right, so we have that y2, y1 are 1, 0, and z is 1. So this is 1, 0, and z is 1. Did some color coding on purpose to show that those columns match up. And in fact, this column also will just be the green. So once we know that, that'll be the same thing. So, well, I guess a different green, right? So sorry, green, but this green. And when x is 1, and this other one doesn't not affect it, right? So this other column we already know already. This must just be 0, 0, 1, 1, because all like this is just a wire connected like that for capital Y1. Okay, so we're just slowly filling it in, right? We just have to keep. We just don't have too much more, to be honest. So the next part. Well, okay. So let's see what the next one is. So the next part will be for inputs present state 1, 0, where x is 0. So similar kind of thing, right? We have this is 1, 0 like that. Just keep track of which one's y2 and which one's y1. And so this is this is going to be 1, 0, which is 1, and so this is 1 again, right? Because this input is 0 here. So we have a 1. And then finally, if it's 1, 1, right, then both of these are 1. So this is also a 1. So this is 0. 0 XOR 0 is 0. And so we have that like that. Right? So this we can just kind of also fill in at the same time. And the very last thing to do is to consider the same circuit now, but with this x now, instead of it was a 0, now we're considering it to be a 1. All right, so we have to fill in this light green column. The two light green columns are the same. So we do the same thing, right? So we do 0, 0, 0, 0. This will be a 0, but this will be a 1 now. So this will be a 1. So this is a 1 and a 1. And then we have 0, 1. So this is 0, 1. So this is 0, 1. So this is a 1. This is still a 1. 1 and 1 is 0, right? 1 XOR 1, I guess I should say, like with an XOR, is 0. So we get a 0 here for our Z values. Then we have the other way around, 0, 1 for reading it backwards, but there you go. And so it's going to be, I mean, pretty much the exact same logic, but just flipped the other way, right? So this is a 1. 1 XOR 1 is 0 again. So we have 2 zeros like this. And then finally, we have the last one, which is 1, 1 for our two present state variables. Here that becomes a 0. This is a 1. So this is a 1. All right. And there we have it, right? So we have everything set up here for us. Right, so this state table tells us everything we need to know about the actual like logical functionality of this circuit, right? It tells us that if we are in state 0 and my input is 0, then I will stay in state 0. Right? If I'm in state 1 and my input is 0, then I'll go to state 2. And so on and so forth, right? Why? I mean, that's just whoever designed the circuit, that's who decided why. And we see that our output does in fact depend on the input. So this is a Mealy machine for sure. I mean, we knew that already, but evidenced here by this. Okay, so we'll just keep moving. So that's our state table. So I know I just said a lot of numbers, right? But hopefully the process is what makes the most sense here, right? Like let's review the process. We were given a table, a circuit. First thing I just organized in the form of an FSM, right? Because that's what it is. Then I, made my table, make table. These are always the same headers, right? Note that it is Mealy. And, make table is a lot of subparts there, right? But 2A is well, 2A is, note that it's Mealy, I guess. 2B is, try all present state variables. And another thing to just note here is just there's some, identical columns, right? There's no need to really, spend so much time doing this. Note that all the orange columns are the same and the pairs of green columns are the same, right? So the orange columns are the same just because of the literal structure of the circuit, right? Again, maybe I can put a little thing like this, right? Like that's what makes the orange columns the same. And this, I'll just do it in green. This is what makes the green columns the same, right? It just depends on if X is 0 or 1, right? That's the only detail here. On the orange section, there's nothing to do with deciding if it's 0 or 1. Okay, there we go. Any questions? Yeah, so someone's saying if you want to make equations and you can solve it faster, yeah, you probably can, right? You can probably solve it faster. So the only part that would really speed up, I mean, it could speed up some parts of it, right? But the part that would speed up is the tracing through the circuit, right? Like you don't have to do these test values. You can just have these logical expressions, but just make sure you're doing it right? So sometimes people find it easier to just trace it through, but yes, of course, you can just construct expressions for your next state variables and your Z in terms of the input and the present state, and that's okay. All right, so now we are going to turn this table, right? I'll just kind of copy the table down now, into a state diagram. Okay. So a state diagram is a typical kind of example of what an FSM does, right? So it's states, and we're transitioning between the states depending on certain conditions. Our states are 0, 0, 0, 1, 1, 0, 1, 1. And let's just take a look at what's going on, right? This is just a representation of this table in things like this. Now, remember, it's Mealy, so our output does not tell us the the present state does not tell us the output. That's what I'm saying. The present state does not tell us the output without also knowing what the input is. So, well, okay, so let's take a look at what's going on here, right? So if we're in state 0 and X is 0, then on the clock, right, we have, so if X is 0, we'll stay there. and Z will be 0 as well. That's this right here. So I'll just kind of color code. Let's do these state transitions just from 0, and then I'll kind of color code it after. So if X is 1 instead, then we go to state 1, 0. So we'll go down here, right? So this is if X is 1, and in that case, Z is also 1. So let me color code this a little bit. We have, I love color coding, so let me do that. These colors are not helpful anymore. So we're here, right? Of course, that's our state 0, 0. The fact that the next state is 0, 0 when X is 0, and the output is also 0 in that case, is that kind of blue arrow. And this orange bit is this. Okay, so just take a second, make sure that makes sense to you. Right, we know our next state information, we know our output information, but they both depend on X, right? So I need to tell you what X is. So this arrow means that if X is 0, on a clock, right? We're in state 0. If X is 0, and then I'll go to the next, on the clock I'll go to the same state, and Z will be 0. But if I'm in this state, and X is 1, then Z will be 1, and if I clock, I'll transition here. Basically, these arrows are telling me what my next state is going to be. It's a little, the best way to understand it is to say that the first thing is like, what's the next state? Or I guess the arrow, right? The arrow is telling you what the next state is. And the value on the arrow is telling you what the current output is. You can say current output. And this is the current input. And of course, with the input, we can control what the next state is, but we can also control the output. That's what makes it a mealy machine. Okay, so then I'll just piece together the rest of the wires here, but I won't color code everything. So if we're in state 0, 1 now, and X is 0, then we're going to go to state 1, 0. So we're going to go down like this, right? And this is if X is 0, then Z is 1. If we're in state 0, 1, and X is 1, then my next state is 0, 0. So this is if X is 1. In such a case, Z is also 1. Then now I'm on the third row. Now I'm here, right? I'm on this one. So if I'm here, then if X is 0, my next state is 1, 1. And my Z is 1. And if I'm here and my X is 1, then I go back to 0, 1. So I'll just just to kind of clean this up a little bit, I'll put this there, and then I'll put this kind of like that. So this is if X is 1, and in such a case, Z is 0. And then the very last row, we're in state 1, 1. Someone's asking for the line going from 0, 1 to 0, 0. When X is 1, shouldn't Z be 0? When X is 1, shouldn't Z be 0? Yeah, that makes sense. That's this value right there, right? We're going from 0, 1 to 0, 0. That means X is 1. So my output Z is 0. Yes, thank you. So then we have just these last ones here, right? From 1, 1. So if 1, 1 and X is 0, I go to state, I go kind of across, like this. So just to kind of not keep everything like a planar graph, then we can just say that this is like that. And so this is if X is 0, in such a case, Z is 0. And then finally, if we're in state 1, 1, and my X is 0, X is 1, I mean, then we stay in the same state, right? X is 1, Z is, all right. And there is our state diagram. So once you have the table, I mean, it's really just creating the graph. It's just kind of rewriting that. Yes, so someone's asking, will it be emailed? Yeah, the recording will be posted today, yes. What's the difference in the state diagram, Mealy versus Moore? I know, like for Moore, something else goes on the transition line inside the bubble. Yeah, for Mealy, yeah, so the difference is that, right? So this is definitely a Mealy machine that we're looking at, right? Mealy machine. Mealy machines have it that, like, if I only, let's do the negative, right? If I'm on a Moore machine, and I tell you the present state is 0, 0, I know the output. There's some circuitry that uniquely determines the output just based off of the present state. On a Mealy machine, that's not true. If I'm in state 0, 1, what's Z? Well, I don't know. Depends on X, right? If X is 0, Z is 1. If X is 1, Z is 0. Right? But just knowing the present state is not good enough for a Mealy machine. For a Moore machine, it is. Okay? So for a Moore machine, instead, just as an example, like this, I'm not saying this is a Moore machine, but as an example, you would have something like, 0, 0 / Z equals 0 or something like that, right? Like I'm kind of just making up a machine now, right? But 0, 1, Z equals 1 or something, right? So this is a Moore machine with two states. State 0 has Z equals 0. State 1 has Z equal to 1, right? And so this is a Moore machine. So you see, you label the outputs based directly on the present state variables. Explain the diagram one more time, sure, yeah. So, no problem. So explain the diagram. Well, we constructed this diagram based off of the table, right? So, I think just really emphasizing the blue and the orange here, right? If you understand that, then I think you understand the whole thing, right? So the blue and the orange is just the very first row. So the blue is telling me if I'm in state 0, and my next state, do you see my mouse moving when I'm pointing? Hopefully, right? I'm pointing with my mouse. Yes, you do. Okay, good. So I'm in state 0. My next state is also 0, but that's only when X is 0. Okay, so then I draw this. When X is 0, my current input 0, my next state is 0, and it happens to be that my current output is also 0. So the arrow represents the next state. The label on the arrow represents the current input, current output. And then the orange is the same thing. I'm in state 0. My next state, if X is 1, is 1, 0. So it goes there. And my current output is 1 like that. So it's really just translating the table into something visual. So you said the diagram, right? Explain the diagram, yeah. And so the rest of the arrows are just doing that over and over again, right? Just constructing those arrows. So hopefully the blue and the orange make sense, right? So if the blue and the orange make sense, then just try to do it yourself. Say, okay, well, I know I see how you turn that first row into arrows. So now how do I turn the second row into arrows? Well, that's what's coming. That's this and this. Those two. No problem. Can we set states to be like S0, S1, A, B, etc., and derive our state table from there, or does all the values have to be in binary? No, it's okay. I mean, yeah, you can call it whatever you want. If you just want to use a label for label A means 0, 0 and B means 0, 1, that's fine. I mean, it's not going to be helpful when you're deriving like next state logic and things like this, right? That's the problem. But I mean, that's fine. Yeah, I mean, logically is the same thing. I don't know if marking wise, I have no idea. I mean, I guess you would, it's multiple choice, right? So things like that don't really matter. So is the X equals 0 the next state? Well, the X is the input. Remember, X is the input in our circuit, right? So I put the X over here. X is just like a switch. Imagine a switch on the board, right? And Z is an LED on the board, right? So X is a switch on the board. The next state is, where the arrow is going. And someone else asking, so for Moore, we won't have next state columns then, right? Well, no, you still have next state. You won't have two next state columns. Oh, no, you will have two next state columns. No, you will. Yeah, you will have two next state columns. You won't have two output columns. You'll have only one output column. That's what it is. So for Moore, you would only have a single output column. I mean, you could make two if you want, and they would be identical, right? Because it doesn't depend on it. So that's your choice. Okay, So, okay, well, anyways, good to keep going. Hopefully everybody's made some sense of this. Let's see what the next question is. Did I lose it? Where did I put it? There it is. The recording will be on my YouTube. Someone's asking. It's just my name. You can just look up my name, Adam Sav, on YouTube, and that's where it'll be. But I'll send an email to my section, and hopefully people can share it after that. Oh yeah, input sequence. You're right. Sorry. Thank you. If the following sequence, somebody has their camera on. I don't know. Everybody check there. There you go. Thank you. If given the following circuit, if the following sequence is applied to X on the input with an initial state here, then we just follow it. I mean, at this point, forget about the whole circuit. Let's just use this diagram, right? This diagram's a way simpler way of doing that. So the input sequence is this. I mean, I'm not going to remember that, so let's just take a little screenshot. So I'll just put that here. And let's do this here. So I'll erase kind of the things that don't really particularly matter, right? So that was just to help for. Okay. So I'm using half gray and half black pen here, but it's okay. I think I can just make it black. Okay. So, well, let's do it, right? Initial state, according to the question, we're in state 0, 1, right? And probably Y2, Y1, right? The way it's written, it's probably Y2, Y1, right? So that's also how I wrote it here. So remember it's Y2, Y1. So we're in state 0, 1. So what I'll do is I'll just draw a little circle for what state we're in. Okay? And the question is, what are we asking? Apply to determine the resulting output sequence on the Z output. Okay. So let's just do it one at a time. This is our X value. And the way I write things is like a little slow because for the point of explanation, right? On the test, you might write things a little bit faster, but at least you have some things going on in your mind, right? Where you can think of, oh, well, we did this in this tutorial, okay, it's kind of like this, right? So it becomes much simpler to do in your mind, these kinds of things. Anyways, it's just kind of a point that's important. So Z, let's look at our sequence on Z, right? So we start in the state 0, 1, and X is 1, so Z is 0. That's this arrow, right? We're in state 0, 1. And X is 1. I haven't clocked yet. Just X is 1, so Z is 0. I clock. Now I'm here. And I'm assuming this is the sequences after clocks, right? So now I'm here. X is 0. Z is 0. I guess I'll just do it in red just so I'm not changing pen all the time. That's this arrow, right? I clock. I'm still in the same state. Now X is 1. Well, cross off as we're going here, right? So now X is 1. So Z is 1. Then I clock. Now I'm here. Did that one. X is 0. Z is 1.
Recording stopped.
Oh, recording stopped for some reason. It's okay. I'm recording on my end. So.
Recording in progress.
Recording in progress. X is 0. Z is 1. We already said that. Clock. Now I move there. We did that. Now X is 1. X is 1 means Z is 1. We clock. We're still in the same state. X is still 1. So Z is still 1. We clock. We're in the same state. X is now 0. So Z is 0. We clock. Now we're in this state. X is 1 again. So Z is 0. We clock. Now we're here. X is 0. So Z is 0. We clock. We're still here. Now X is 1. So Z is 1. And we're done. Right? So technically the state we end up in is 1, 0. Doesn't really matter. Would you ever read the sequence backwards? Would it change it or no? Like from right to left, left to right. Yeah. I get it. Yeah, right. So it's like, which way are you reading? Again, like a thing like that is something you write on the test. You say, I'm reading it from left to right. You just say it. Now, I mean, we always read it from left to right, right? Like in general. Of course, there's questions about like when you write MSB, LSB. Like I understand there's always like a confusion about things on the left or the right side. But like if you write a sequence of numbers, like if it's called a sequence, right? Like the sequence goes like, you know, like 2, 4, 6, 8, 10. I don't know, right? This is 10. This is a sequence, right? I mean, you wouldn't write 10, 8, 6, 4, 2. I mean, you could, but, and that's the whole thing, but sequences, the word sequence is the kind of key thing here where really that is always from left to right. How come we didn't need to know the behavior truth table of the D flip-flop as well? Does it not matter what flip-flop it is for this type of question? Yeah, it does matter. If you put a different type of flip-flop, it definitely does matter, right? But, well, the structure of it here is as a D flip-flop. Usually for FSMs, we always use a D flip-flop. For other types of questions, you would not necessarily treat it like an FSM. I mean, you could. You can make FSMs with other flip-flops, but you would not necessarily treat it as an FSM. And you just have to maybe more organized, in an organized way, kind of just trudge through the logic of what are all these different options here. But similar stuff, right? Yeah, we didn't need to know what the next, I did implicitly use the fact that these are D flip-flops in the fact that I said that my next state variables are whatever the input is here, right? I said, yeah, I didn't really say it, I guess, but my next state, my present state variables, but in the next state, so my next state variables, right, my y1, is by definition not what's on the left side of this flip-flop. It's what my little y1 will become next clock. For a D flip-flop, that is what's just on the left side of this flip-flop. So let me just, to be clear, right, like y1 is what y1 will be next clock. For a D flip-flop, that is just what is on that side. That is y1, if this is little y1, right? For a T flip-flop, well, you know, then we maybe have some more logic. It's not, you know, necessarily going to be whatever is here, right? There's some circuitry here, right? And this will be this little y, capital Y1, which will be our Y1 eventually, right? I mean, we'll output our what the next state is, and it will become, there's nothing here. It's just a wire, right? It's just like a logical value here of becoming the present state variable. And that Y1 could be more complicated depending on the T flip-flops. When we do FSMs, it's nice to kind of just structure it with D flip-flops. You have other kinds of flip-flops for other types of circuits as well. Okay, so kind of a long question. We spent an hour almost on this, but anyways, we keep going. So there we go. So that's we derived the state table and the state diagram, and we saw what it was like to follow a sequence. Note how I did it, right? Like I thought about what state I'm in. I thought about what my state transition is, and then I always keep in your mind, right, the sequence of clocks. Clocking a circuit is like a moment in the circuit where everything changes, right? That's the instant. It's a synchronous point where everything changes. So when you do that, that's when your transitions will happen. So just keep in your mind, like, when are you clocking, right? You clock the circuit at a certain moment, and that's when things change. And so we had to clock it, you know, whatever, 10 times here. Do we always start at 0, 0, state 0 when we follow these sequences? No, I told you in the question, start at initial state 0, 1. And if they don't say it, then say, I'm starting in state 0, 1, or 0, 0, or whatever. Just start in whatever state, but just, you know, probably the 0th state is probably the one that makes the most sense, but just say it. If it was negative edge triggered, would anything change in this case? No, it would not. Then can we, sorry if I missed a question. I hope I didn't. How come we didn't? No, I think I'm okay. Can we also determine the waveform based on the given X? it's 10 bits and initial state. I mean, yeah, right, sure, right? You can draw the waveform now for this, right? I think that's part of the next question. No, the next question 3. We can do a waveform question if you'd like to do a waveform question. So we could do that maybe. Yeah, what happens if one of the clocks of the flip-flop is high active and one is low? Yeah, so that's like an asynchronous circuit, right? Because the clocks don't happen. They're technically connected to the same clock. Yeah, that's kind of complicated, right? They're technically connected to the same clock, but they don't clock at the same moment, right? So this is like, what you're describing is like when we talk about RAM, we have like DDR4 RAM, right? This DDR stands for double data rate. That means it activates on the rising edge and the falling edge as well. And so what you're describing is more complicated than what we see here. We deal with pretty synchronous circuits and things like this, right? So that means all the circuits kind of clock at the same time. So weird things will happen. What would an example multiple choice question look like since there are multiple? Yeah, I appreciate your question. I don't know, unfortunately. You know, there could be. I don't remember I didn't see your midterm, so I don't know what kind of questions you had on the midterm. When I took this course, it was also multiple choice. I think just the midterm was multiple choice. No, maybe the final as well, actually. The final was multiple choice. I don't know. Yeah, so, but it could ask for a column here, I guess. I'm just making up things. You would know better than me because you took the midterm. But, like, you ask for a column here maybe, or it could ask for, generally what it would, my understanding is that it'll ask you to do enough work that you're basically doing the full question, but then you just submit your answer as a multiple choice solution there like that, right? So, yeah, so it's important to keep organized and be able to do the whole thing because you could be asked about any part of it. So yeah, okay. So anyways, that's that question. Let's keep going. Let's take a look at another question here. So given the following state diagram, yeah, let's do another kind of. This is a typical type of question. We might just do. We might just do the beginning and just ask for if it's Mealy or Moore. The next part of the question is design and draw the circuit. So anyways, let's just first decide if it's Mealy or Moore. Well, I mean, it should be kind of clear, but based on our discussion above here, given the following state diagram with X as input and Z as output, right, indicate the model. So is it a Mealy or Moore model? And there's our reset, right? I guess I could put that in the diagram here too. You could put a reset there if you want. Anyways, so what are we thinking? Mealy or Moore? Anybody want to suggest? Does the output depend on the present state solely, or the present state as well as an input variable? So everybody's saying Mealy because it's the same kind of situation as this, right? Moore would have the output variables just linked into the present state because they only depend on the present state. So of course it's Mealy. Okay, and then like the question here is like the other way around, right? Turn this into a circuit, right? Turn it into a circuit that does something. That does this, not just something. So, well, we can do that, right? That's part B, is design and draw the circuit. Now, I don't know, we could do the whole thing if people are interested, but just a general framework of how you would do something like this is you would make, make the state table, compute next state logic functions, compute output logic functions. So this is like K-maps, right? K-maps. This is also like K-maps. And then draw. This was a mixture of I think lab 5. Yeah, lab 5. No, lab 5 needed to do stuff like this, right? Because you had an FSM in lab 5. So I was gonna say lab 5 and 4, but no, just 5. 5? I think so. Whichever one was the FSM lab. And so you did this one in the FSM lab. This one you didn't really have to do, but it's not much harder. Actually, just literally 1 bit harder. And then you have to draw it. So we kind of did that in the lab as well. So, I mean, we can do it, but we did just talk about FSMs for a long time. So I thought maybe we could, I mean, this next one's also vaguely FSM-y, but we can look at this one. Still have some time. Is there VHDL on the final exam? Were you told this? There's VHDL? Yeah. Okay. So why don't we do a question like that next? Let's do a VHDL question. And then we can see what, and then we can maybe do a signal question after, like a waveform. So let's do a VHDL question just because they said there would be VHDL. It's not going to take very long. So this question here is just asking, which circuit does the following VHDL code represent? And then it gives you a bunch of VHDL code. Again, we're trying to understand this. We have to understand the structure of VHDL, right? The very first thing is don't whatever, right? I shouldn't highlight it. I mean, I really just these are all just part of syntax of VHDL. It doesn't help us understand what's actually going on, right? So, I mean, it has to be there, but it's not super important. The tabbing tells us what the nested behavior is. We also don't care about this, right? So just immediately start just removing things that you don't care about. Okay, so we've kind of narrowed it down. All this up here, right, is just all about the ports. And then again, like this, we don't really care about this. We don't really care about process. I mean, I guess kind of important, but I guess it doesn't really matter. This we don't really care about. This is just telling us what's happening, right? This is the actual functionality of the circuit, right? So really there's only a couple lines here that matter. So let's understand. Entity circuit is, then it describes our ports. Generic and integer defined to be 4. This is just some syntax, but I think it's, even if you've never written this in VHDL before, I mean, I think it's clear that it just means n is 4, right? Capital N means 4. Okay, then what do we have? R is a logic vector of length 4, right? 3 down to 0. L, E, and W are just single bit logic, STG logics. Clock is obviously just a clock, and then Q is a buffer, right? Which is kind of somewhere in between just can be used as a port in general, as a port, a buffered port. Which is also just let's just say 4 values, right? It's also just a collection of 4 values. And we can see what happens to it here, right? And you can think of it as input or output. Okay. So it's kind of like a signal internal. So what I'll do to understand this, right? We have to try to understand. So of course, n is 4, right? So that means that this R here is 3, 2, 1, 0. Right? It's R3, R2, R1, R0. Then we have L, which is some value, just a single value. We have E, which is just a single value. We have W, which is just a single value, whatever, just a single value. We have clock, which I'm not even going to, clock, you don't care about the value of the clock, you just care, you can see in this very first line here, right, that wait until clock event, clock has changed, and clock is 1, so it's a rising edge, right, so we don't really have to care about that. And then Q is this buffer, but whatever, it's also 4 values, just like R is, right? So maybe I'll actually put them together. There are 2 kind of vectors, and then L, E, and W are our here. Okay, someone asked me, can I explain what it means by vector? Well, vector is what it means. Well, vector means a lot of different things, but a vector just means a list of numbers, right? Like if you might think of a vector as like an arrow, but it has 2 components, right? So it's just 2 numbers. So a general vector is just a list of numbers. So that's all they're saying here, right? It's just a list of numbers. Okay, so Q is also 3, 2, 1, 3, 2, 1, 0. Okay, and now we have to think about it a little bit. Like we don't know any of the values here, right? When we're going through this process, but we could just pick some values and we can see what happens, right? So first of all, if E is 1, then, and then all the rest of the code. So that tells me that E is an enable, right? So that's, I think, clear, right? So we've deduced that this is an enable. And probably we should just set that to 1. Because if it's 0, then it does nothing. Okay, which is what an enable is. Okay, great. So we can do that. If L is 1, then do something. If L is 0, do something else. So L seems to be some kind of control signal, right? It's controlling the behavior of the circuit. If L is 1, it does this. If L is 0, it does this. Okay. So let's first think a little bit about what happens if L is 1. If L is 1, then Q just becomes R. Right? So if L is 1, then this is what happens if L equals 1 on the clock. Okay. So basically we have this R maybe register, that might be something to think about, R for register. If L is 1, then it just parallel shifts into Q, all values. Okay, it's fine. If L is 0, then what happens? Then Q0 becomes W. So let me use a different color here, right? This is if L is 0. Q0 becomes W. And this is like, we're splitting this between 0 and 1, right? Maybe this is like a control signal, 0, 1. And okay, so what happens? So that happens. Then, okay, some syntax that maybe you've never seen before, but what could it mean? What could it mean? For, well, it's probably a for loop. End loop, great. Okay, so it's definitely a loop, right? So I in 1 to n minus 1. Remember, n minus 1 is 3. Okay? It's 1 to 3. So I is just a for loop. I goes from 1 to 3, inclusive. And so this means it's just like a way of writing this kind of lazily. Well, not lazily. I mean, we'll talk about that in a second, but automatically. Q1 is Q0, Q2 is Q1, and Q3 is Q2. So this happens first, right? And and this is also like on the clock, right? Like this happens. This isn't like 3 separate clocks that make this happen. This is all on the clock. So yeah, so breaking this up into a couple of statements here is this, right? So if this is all just kind of like rehashing this, like maybe I'll just kind of like put a little bracket and put a little star and put a little star, right? This is just like Q1 because it's I in 1 to 3, right? Q1 attains the value Q0. Q2 attains the value of Q1. And Q3 attains the value of Q2. Q is being, someone's asking for L equals 1, is Q being assigned the value of R, or is R being assigned the value of Q? Q is being assigned the value of R. Both of those are 4 bits. So hopefully that's clear. Okay, and then again on the clock, right, what's happening? This bit is being sent here, right? That's what's going to be the value. And at the same time, the values here are going to be shifted over, right? So Q0 is going to be moved into Q1, Q1 is going to be moved into Q2, and Q2 is going to be moved into Q3, and Q3 is just overwritten, it's just lost. Remember, this doesn't happen in 3 separate clocks, this happens all in one clock. So it's like, you might think to yourself that this is all just going to be W, right? but no. It's just all the values get shifted, and the W gets placed here. It doesn't really matter what order you put that in, okay? Because it's describing to you basically what's going to happen on the clock. And it happens to everything synchronously. Okay, so now we know what it does. L is kind of a control signal. So yeah, so why wouldn't all the values be W? Someone's asking it. It's a good question, right? So the main thing is that this is happening in one clock. This is happening at one instant, right? If L is 0 and we're in this kind of, in this state here, it doesn't matter the order you would write this in. You could put this Q0 is W at the very end, and everything would be the same. And it's because everything's happening, these assignments don't happen in sequence. These assignments happen at the same moment. So that's important. Right? The assignments don't happen in sequence. The assignments happen at the same moment, synchronously. So when I'm doing this red arrow, moving the value from Q0 to Q1, W hasn't been written here yet. And when I'm writing this value, right, from 1 to 2, Q1 to Q2, the value of Q1 hasn't been written yet. I'm still using the old value for Q. So that's the important thing. I'm still using the old value for all updates here. So hopefully that makes sense. Okay, well, yeah. So what is how would you describe this? What does this circuit do? That's just how VHDL works. That's like we're describing, this is what happens at one clock event, right? At a single clock event. If it happened in sequence, we would need multiple clock events to happen for the signals to settle. Can I explain why W gets shifted in the box Q? So there's a few things you could be asking, but how does W get into Q at all? From this first line, right? That's how W gets into Q. Which means that on the next clock, the value of Q0 will be W. But then eventually, as I keep clocking, this value of W will keep shifting, right? Over and over again here, right? I mean, if I clock 4 times, then it'll all be W if I don't change W. If I keep W, just wire this to 0, let's say. After 4 clocks, it'll all be 0. So someone's asking, well, someone's suggesting, could it be a bit shifter to the left when L is 0? I agree. And then when L is 1, it's something else, right? But all related. So I agree. Right? So this would be like a 4-bit shift register. That's what happens when L is 0. L usually stands for load, to load in a value. So what we're saying is that this is a 4-bit shift register with W as the input bit. Because if you have a shift register, then you have to know shift register means all the bits are shifting left or right. But no matter if you're shifting left or right, doesn't matter. You're always going to be losing one and gaining 1 bit every shift. We're losing 1 off the left, and here and we're gaining 1 off the right. So a shift register needs always the W as needs an input bit. So it's a 4-bit shift register with, and this is the important thing, when L is 1, that's like a load operation, right? Parallel load controlled by L equals 1. So if L equals 1, that means on the next clock, we're doing a parallel load. Everything from R, let's say from R, which is one of the inputs, right? Everything from R is being put in to the Q signal, right? It's called a buffer, right? So you call it an output. It doesn't really matter. It's just like a signal internal, some pins internal. They could be going to the outside of it if you wanted to. It doesn't really matter. So this, I think, would be my final answer. A 4-bit shift register with W as the input with parallel load controlled by L equals 1 from R. Okay, what does the wait until keyword mean in VHDL? Does it mean we have to wait for clock to occur, then everything else occurs below? Does this affect the functionality of the code? example, only after 1 clock something happens, or do we wait? Does it mean that we have to wait for a clock to occur, then everything else occurs below? It's like a break point in the code, right? So it's like a wait or a sleep statement in C, right? So it's like the process will sleep until the first time this will happen, right? And okay, yeah. So this is the important thing. Remember, when we're in a process is like a while loop. And effectively, okay, so a process is like a while loop. A process has like what's called a sensitivity list. And the sensitivity list of the process means anything in that list, it's a bunch of input ports. If anything changes in any of those ports in the sensitivity list, then, okay, trigger this. Process will happen immediately. So what we're saying is that if any value in R, L, E, W, or clock changes, notably the clock, but if any of them happen, start this process. And the very first thing is that actually, hold on, we don't want anything to happen, because what if just R changed? What if the value of R changes here? We don't actually want anything to happen until a clock event, until we have a rising edge of the clock. That's kind of the point of synchronizing the circuit, is that we have everything kind of synchronized here, that nothing will change until this moment. So hopefully that gives you some kind of answer, right? So yes, it does affect the functionality of the code. If you removed that, well, if you removed that, you'd have a lot of problems. The circuit would be very, would be very quick to react, right? Like you have no control over when Q gets shifted or anything like this, right? Or when does the shift happen, or when does the load happen? You have no control over that. It just will happen kind of randomly and continuously. So yeah, okay, I don't know. That's my answer, hopefully. Parallel load means like this entire 4 bits are being loaded at the same time. It's compared to like a serial load, right? So a serial load is effectively what we have with the W. So a serial load is like, I'm just telling it to you 1 bit at a time. A parallel load means I'm telling you 4 bits at a time what needs to be in there. So really, in a way, you can think of this as a register that has both parallel load and serial load. The parallel load is just a functionality here. A serial load means I'm just like, let's say I want 1010 in this register. Okay, well then I'll make W 1010, right? But it's going to take 4 clocks. That's the thing. That's the serial load. Serial, like with an S. The parallel load, I'm just going to say 1010. And then there we go. What does the red lines shifting mean? Can we say that W is iterating until 3? Well, the red lines shifting is this whole segment here, right? It's like I just mean like the value that is in Q2 will be, maybe I'll say it again. The value in Q3 will be the value of Q2. I don't know quite what you mean by iterating. W is iterating until 3. Like after 3 clocks it will be, right? But that's not in 1 clock. In 3 clocks it'll end up there. I'm just talking about 1 clock here. That's kind of separate. Oh, sorry if I missed a question. My bad. I don't know if I did. I guess I missed it. Yeah, not sure. Would Q0 remain the same always since the loop starts at Q1? If W is staying the same, sure. But remember, W can change between clocks, right? Like imagine W is like a switch on your board, right? So, like I was saying with the serial load, like you can change W. Right? So if you change W, then then you would have that value going in here, right? So you might have a sequence W1, W2, W3, W4. So right now it's like W1 is being put here. Next clock W1 will be here and W2 will be here. W2 can be different than W1. That's just like you're deciding what inputs you want to have for W. Just like all these R's, like you can choose whatever you want for those values. Hopefully that makes sense. Okay, I'll pause here for a second just in case anybody has any questions. I know we said we'd do a break, but let's just not do a break. I started a few minutes late, so let's the final answer I wrote is a sentence right here, but the value of Q0 never changes. It can change. Why not? Why do you think it can't change? I'm like, you know, genuinely, right? Like we have Q0 here, right? It can't like, yeah. Let me draw a picture here. Let me draw a picture, and I think this. But yeah, like, what's leading you to believe that Q0 can't change here? I'll draw, I'll draw a picture. So there's our circuit. These are our Qs, right? So this is Q0, Q1. Well, I'll draw it like Q0, Q1, Q2, Q3. And then this is like our Rs, right? So this is like R0, R1, R2, R3. This is like W. This will be our clock. And let's just say, you know, obviously enable is fixed to 1. And so, you know, let's think about what's happening here, right? So I'll draw a little like clock here, right? So on the first clock, right? This is the first clock. Before the first clock, let's say, I have an L as well, right? So let's just say L, I'll just fix that to be 0 right now, right? Then we don't care about any of the values of the R's, right? If L is 0, we just care about W. So if W is 1, and let's say there has to be some beginning state here, right? So let's just say it's all 0. Who knows? Let's just say it's filled with zeros to begin with. Then after the clock, it'll be, so this is the first clock, right? This is the first clock. After the clock, it'll be 1, 0, 0, 0, right? Because that's the whole point of the circuit, right? Is that the value of W gets funneled into Q0 there. Then, and again, we don't care about these values. Let's say I switch it to a 0 now, before the second clock. Right, let's say I switch W to a 0. Or no, let's say I keep it at 1. Let's say I keep it at 1, just for this one. Then after the second clock, right, it'll become, that 1 will appear there. This 1 will shift up. This 0 will shift up. This 0 will shift up. So it'll become there. Right? Maybe I'll use another color. So it'll be 1, 1, 0, 0. Now let's say I switch it to a 0. That's the third clock. Right? On the third clock, those 1s will shift up. So 1, 1, that 0 will shift up. And now I have a new 0 coming in. Right? So maybe I'll just do a little highlighting here. So that 0 is that 0. That 1 is that 1. I should use different colors, but anyways, that 1 is that 1, and that 1 is that 1. Sorry, I kind of screwed up the colors here a little bit, but hopefully that makes sense, right? So Q0 is changing. Q0 is going 0, 1, 1, 0 here like that, because W is changing. This is just some examples. Okay, perfect. I'm glad that made sense. So we know this is a shift register because Q goes in the red arrow direction at L equals 0. Yes, that's what a shift register does, exactly. Shift registers like shift everything to the side. Yes. Correct. What you're saying is correct. Okay. Last chance here. Anybody have any questions about this one? Okay. Well, I'll give you a second to type if you do, but that's that. Now let's few things here. I think we should try to understand a signal question, like with a waveform. For question 2, will answers be posted? I will not be posting any answers for it. I don't know if they exist online. I'm not sure, but I will not be posting. because I haven't written them. Okay, let's look at this. And importantly, they start you off a little bit. Okay, so sorry, someone's asking, in general, when will you use an excitation table? Excitation table is kind of like a way, it's like an informal way of describing like what flip-flops do, right? So it's like what the description of these synchronous circuits are based off of the inputs. Excitation means it's like whenever it's triggered. So you have a rising edge trigger, or you have a falling edge trigger, or whatever trigger. But just whenever it's triggered, that's like the excitation table. And it's just kind of an informal kind of table to describe what's going on, because we don't know specific values a lot of the time. But that's pretty much it. Could I ask where you're getting these questions from? I'm having a hard time finding practice. These are just generally people who have sent me these questions, and they're just, you know, what I found available online and things like this. So that's about all. Okay, so let's try this. So it says, given the following circuit using a 1-bit adder and using a 1-bit adder. Okay, so there's a 1-bit adder. It's a lot happening, right? Like so many blocks and wires, but I think it's not too complicated. So X1, X2 are inputs. There's a 1-bit adder and there's a register. You know, a register is just a collection of flip-flops, right? So here we have some presumably D flip-flops, I guess, because of the way that they have written it. So with that in mind, let's take a look at what's going on here. So we sketch the correct output waveforms at C in, C naught, C out, I guess, S and Z. S is our sum and Z is like our output variable. Oh yeah, sorry, I guess I was looking at it backwards. It is a D flip-flop. It's going in this direction, right? It's going backwards. Just kind of wrote it backwards. And yeah, okay, so and so in their proper time relationship in the following input waveforms. So of course you have to be told certain things. So what do you have to be told here realistically? You have to be told the values of x1, x2, okay. The value of reset, given that. The value of clock, okay. And that's it. Because everything else is internal signals, and Z is an output signal. So sometimes it's helpful just to like put a couple arrows just to remind yourself what's happening. So like, yeah, Z is an output signal. These are output signals. These are input signals, right? Z is an output signal. Input, right? This is going out, right? Just to remind, because especially in a situation like this where it's like things are kind of turned around, right? Clock is of course an input signal. So hopefully the flow makes sense here now a little bit more, right? Of what's going on. This is of course an input signal. They drew this kind of backwards for some reason. Anyways, so now we want to follow this waveform, and we are given those things that I was saying that you need. Well, we were given them. We were given the value of clock, reset, x1, x2, and so on. Yeah, so you can find the rest of the things. Okay, so let's do it. So, you know, C in, blah, 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 C in, C out, S and Z are the values we need to find. At this instant, this is like a low active reset, right? So it goes low, it resets. And then it's high, so we're not resetting anymore. The values of x1 and x2 are both 1. And we can assume that the reset position, well, it says, what does it say? Both flip-flops are initially reset as indicated. I think they mean by that, like that. Right? That means that both flip-flops have been reset, which we can assume to be like a 0 position. Right? We can assume to be like a 0 position. So what we'll need to keep track of a little bit here is the signal, this signal here as well, right? Which is like our C in signal, which actually, sorry, I guess we do have. We have C in here, right? So never mind. We don't have to keep track of that particularly. I mean, we have to keep track of it, but I thought we'd have to like kind of draw it separately, but we don't. Okay, I'm going to be doing a lot of scrolling up and down, so maybe I will, instead of doing a lot of scrolling up and down, I'll take a screenshot of this and just put it like here. Maybe like that. Hopefully everybody, and it's getting a little messy, but hopefully everybody's okay with this. Kind of bring it right up to the edge there, like that. Okay, so hopefully everybody's okay with this. We can kind of see everything. I don't have to scroll so much. So, you know, work with me here. Let's try to do some of this together, and let's see what we can come up with. So we have, at this moment, the circuit has been reset. So that means that these values are both 0. And so immediately, you know, what's my Cin? Well, Cin is the value of y0, right? Maybe just let's note this right here. Cin is y0. And Z is y1. Write that actually maybe in front of what they actually are. So Cin is y0. Z is y1. So that just helps us with these. There are these internal signals. Remember, like a FSM like this will have two, you know, in this case, there's 2 flip-flops, so there's 2 state variables. And since there's 2 state variables, we'll have these 2 signals, which could be another signal on the waveform, but we don't usually draw them. That's not really part of the ports of the circuit, right? It's an internal signal. But we do have to keep track. And so here, luckily, we have some way of keeping track nicely. Okay. Yeah, and you know, I can't help myself but to color code them. So let's color code it a little bit like this, right? So those are the same, and these are the same. Okay. So Cin, which is the same value as y0, is of course 0, right? Because at the moment of this reset, I mean, there could be some kind of weird thing happening here, right? Like we don't know what's going on for that moment, right? But after that, we definitely know Cin is 0, like this, right? But just to simplify things, right? Whatever, Cin must go to 0 at that moment. Then let's think about these other values, right? So C out, well, what's C out? C out is not related to any kind of reset, is not related to any kind of clock signal. It's just the C out from computing X1, and it's a 1-bit adder, right? 1-bit adder. So it's just adding these 2 signals. 1 and 1 makes, let's use our table quickly. I mean, obviously, I know what it is, but you know, let's just remember. So we have 2 input signals. We have A, B, just so I don't have to repeat this over and over again, right? So we have S and C out, right? So 0 plus 0 has a sum of 0 and a carry of 0. 0 and 1 has a sum of 1 and a carry of 0. 1 and 0 must be the same thing. And then 1 and 1 has a sum of 1 and a carry of 1. Okay, so we have these 4 values. And so, well, then everything else kind of follows from that, right? So 1 and 1 has a sum of 1 and a carry of 1. Well, it would just stay like that, right? Because the X1 and X2 are not at all clock synchronized, and I mean they might be, but the C naught and S are not clock synchronized. Anyways, and then the Z is just the value of Y1, right? And Y1 at this moment will switch to 0 because it's being reset, right? So there's all our signals before the first clock, and then boom, we clock it. Okay. So there's a couple more connections we can make here, right? Because what's our next state variables? Well, Y1 will be the value of S, right? So this is kind of going the other way. So how about I just really notate this properly, right? Like this is going like this is going like this, right? Here, Y1 is becoming the value of S on a clock, right? Whatever S is, that's what Y1 becomes. So that's this connection that I'm drawing right here between S and this right here. And similarly, y0 becomes C0, C naught, right? Like output, carry out. So many ways to say it, but let's just pick one way. So I'll probably keep saying C naught just because that's the kind of what it looks like to me, C naught. But it's a carry out. Okay, so we have these relationships, and this tells us what's happening on the clock, right? Because we want to know what happens to y0, y1. Well, on the clock, right, y0, right? Okay, someone a question for the adder. Why is the output 1 1 for AB is 1? Well, yeah. So, well, there's a lot of ways to kind of phrase it, but is that not right? Did I do something wrong? No, that is right? Because we have sum is 1. Oh no, sum is 0, right? Wait, sum is 0. Yeah, 0 1. My bad. I don't know what I'm doing. Sum is 0, and the carryout is 1. My bad. There you go. That is correct. So then, yeah. Then we have to adjust this here, right? This becomes a 0 like that. Yeah. Of course, because the sum is the XOR, right? And the C naught, the carryout, is the AND of the two. Apologies. And so the sum is going to be just a 0 there for the inputs x1, x2 being 1. Okay, so what happens on the clock? Let's just go part by part here. On the clock, C in, right, becomes whatever C out was, right? So in a way, what I'm saying is that this transitions up to here. So this becomes a 1 here like that. What I'm saying is that this value transitions up to here. Okay, fine. We won't deal with this just for a second. Okay, let's not deal with just for a moment. We won't deal with this one. The sum, we also won't deal with for a second. The Z, the output. Well, the output is just whatever y1 is, right? And y1 is just the sum from the previous step, right? So the sum from the previous step was 0, and that will transition here to become a 0. So I'll draw it kind of like both, but I'm using the colors to kind of just remind why, right? So that kind of goes there like that. This other stuff, the carryout and the sum, well, that depends on x1 and x2, right? So now it's 0, 1, right? So that means our sum is 1 and our carryout is 0. So our sum is 1 and our carryout is 0. And in fact, we can compute, we may as well just do this now. Let's just compute the sum and the carryout, right? At all the clocks, let's just keep going through it, right? Because that doesn't depend on anything else, right? Oh no, sorry, it depends on Cn. My bad. It depends on Cn. Hold on, it depends on Cn. That's why I forgot. It depends on Cn. So the sum here is going to be, right. I have a Cn that I have not accounted for in this table. That's why I'm getting confused. So our Cn Yes, correct. Someone's just suggesting exactly what I'm doing right now. So if the Cin is a third input into our adder here like this, right? It can have all these kinds of values. So this all what I've described here is for Cin being 0, and then we're going to have another set of 4 for Cin being 1. Right? So we have 0, 0, 0, 1, 1, 0, 1, 1. Okay. So this is going to be 1, 0. This is going to be 0, 1. This is going to be 0, 1. No. This is going to be, yeah, that's right. 0, 1. And this is going to be 1, 1. Okay, there we go. We got it. Please correct me if I'm forgetting something, but that seems right to me. It's just the negated version. And so if I have just 1, it should just be the sum is 1. If it's 2, right, this is going to be 0 with a carry of 1. 2, 0 with a carry of 1. 3 is 1 with a carry of 1. So that looks right to me. Now, So yes, now we have this situation. And so this, okay, so now we can finally kind of compute this, right? So the value of C carry out is, so we have, this is going to be like, let's just call this our x1, x2, and C in, or we could do x2, x1, doesn't matter. X2 and x1. Now let's just do x1, x2, just because that's the order that it's written in. So x1, x2, and C. It really doesn't matter. They're the same. It's kind of arbitrary here, right? And it's like symmetric in these inputs, I guess is a better way of saying it. So it's going to be 0, 1, 1. So 0, 1, 1 is 1, 0. I guess I maybe should flip those two columns, but it's okay. 1, 0, like this, right? And again, on the state transition, the same thing is going to happen now, right? So the value here, right, is going to transition into what's here in the next clock, right? So on the clock, right, C in becomes whatever Y0 was. Right? So we have these values. Let's just, make sure everybody's following so far. Pretty good, right? So, right, the values of C0 and S, the carry out and the S, depend on these values. The value of C in depends on the internal state of the circuit, so we have to kind of update that as we're going. Okay, and so now we're here. And then on the clock now, right, what we have here we have a 1. On the clock, C in will become a 1. I mean, it was already a 1, but it's gonna keep being a 1. Like that. How do we find the first part for C in, like this little dip right here? Well, we said that the flip-flops are reset as indicated, whatever, so they're being reset. So if the flip-flops are being reset, that means the outputs are being set to 0, right? They're being reset, so this is a 0 here, and this is a 0 here. That's what I wrote there in black, I guess. So if set to 0, that means it's being reset, so it's set to 0 there like that. That's why Z is also being set to 0. Okay, and then again, on the transition, right, this value here will transition to below. So this will transition like so, right? It'll kind of continue. And then again, we can compute C0 based off of the values here, which are 1, 0, 1. So 1, 0, 1 is going to be, I kind of have it flipped, but it's going to be 1, 0, just in order here. It's going to be 1, 0. So this is 1, 0. So nothing particularly interesting happening just yet, but let's see what happens next. So this will transition here, right? So again, I know it's kind of weird that I'm using two colors, but hopefully the black is kind of like the answer, and the colors are just a little bit help. The value here, the value here will transition here, right? And then again, we have to compute things. So it's 1, 1, 1. 1, 1, 1 is 1, 1. So this will be this will now be a 1, and this will transition into a 1, like that. And then we continue. The value here will transition into the value here just by the flip-flop. And the value here will transition into the value of Z, again, just by the flip-flop. Okay. And then we have to compute again. 0, 1, 1. Okay, 0, 1, 1 is 1, 0, right? I have it backwards, but it's okay. 1, 0. And then we continue exactly as we're going, right? So this will transition up. The value for the pink one will transition down. Coincidence that's also going down, right? Like lowering the edge. And then here we have 0, 0, 1. 0, 0, 1 is right there, which is 0, 1. So this becomes 0, 1. then this value right here will transition up here. Am I basically just following the truth table? I'm following the truth table. The truth table is being used. This truth table is being used for these values, and that's it. Then on the clock, what's happening is that the value, what I'm trying to indicate with these little, with the colors, is that the value, like on the clock, because of the flip-flops, gets transferred over, right? So, sorry, that's wrong then. I don't know what I'm doing. So that will, I guess I just got distracted. So this will go here. Like that's how I can determine that so quickly, right? And then similarly here, this value, so these values have all been kind of going like that. And again, it's just the structure of the circuit. It's based on these equations that I wrote right here. It's because the structure of the circuit. And then one more time here, that will transfer there. But now to find C0 and S, I need to actually add 0, 0, 0, right? Sorry, hard to follow. Yeah, 0, 0, 0, which is of course 0, 0. So this will continue to be a value 0, and this will switch to a value 0. And then here I'll just transition one more time. So this will go here, and this will go here. And then finally, the value here will transition down, and this will go here and here. I know I'm saying here and here a lot, but hopefully you're following the picture, right? What's going on? Okay, on the first clock, X1 high or low? On the first clock, X1 is high. At the moment of, yeah. They should do it a second later, but yeah. At the moment of the first clock, X1 is high. It's like the edge is like there, right? Like that's where the edge is. Yeah, it's not like this. Like in practice, like you put it there, right? Like, because actually on a transition, like nothing actually goes like that, right? There's no electrical signal that does that perfectly. Everything's like this really, or it could be worse, right? So how we write it usually is something like this, right? So you kind of you do this, but you have this kind of period in between here that you don't know what's going on necessarily. But that's more of a technical detail, yeah. So they mean this. Okay, and then sorry, I guess there's one more row, which is just here, not row, but one more entry, which is here, and that's just for 0, 0, 0, which again is 0. And that's it. There's no more. So to summarize, C in follows C0. C in follows C0 from the previous clock. Z follows S from the previous clock. Yeah, exactly. And how do I know that? Well, that's not always true, but that's just true based on the circuit here, right? What do we say? C in follows C0 from the previous clock. That's the point of the flip-flop, right? C0 from the previous clock is being sent to C in. And then S from the previous clock is being sent to Z. And that's the point of these arrows here. Can I explain why we made a table including C in? Well, but that's the functional table of this full adder, right? This is a full adder which adds three bits at a time. Right? It's a 1-bit adder. Like the number of the size of each input is 1 bit. But you need, whenever you're adding, you're always adding 3 things. Okay? I mean, it doesn't feel like it, right? But if you're adding 2 plus 6, in general, you really mean like carry in 0, right? Carry in 0, and then add 2 and 6 is 8, right? So the carry in is always implicitly there. I guess that's my answer. What was the order of the variable bits you looked at from start to end, and how did you start at the beginning to continue forward? What was the order of the variable bits you looked at from the start to end? I'm not sure I understand. Like these are the. I started with these because that's what they like. They gave me the first four rows, right? Yeah, and then. Yeah. The whole process. What was the order of variable? How did you say? Oh, where do you mean the whole process? Could you rephrase what you're saying there? I'm not sure I fully understand. What was the order of the derivatives? Well, continuing forward, I mean, was just the structure of the circuit, right? Based on like the clocks of the flip flops, right? So that's kind of continuing forward. The values at the beginning was given to us by the structure here, by the diagram. So they gave us the values of x1, x2, and that's all that really matters because then we're resetting, right? And so then we know these values here. Like, how do you know? And I'll get to everybody's questions. Yeah. How do you know? Like, how do you know you determine C in first, then Z, then? Well, I guess that's kind of following it in the circuit here, right? So, to be able to figure out, like, let's just say I want to find any value here, right? Like, if I want to find the value of S, okay, then I have to look at this circuit. And I have to determine the output of this circuit. Well, the output of this circuit depends on A, okay, but that's known. That's given to us. Depends on B, okay, also known. And also depends on Cn. Okay, well, I have to find Cn. What's Cn? Cn is known as well because the circuit reset here, right? So I guess one way to think about it is just start from what is known. I know the circuit reset, so I know that these are both zeros. So what does that mean? Well, it means Z is 0, and it means Cn is 0. So naturally, we have this order of finding the present state variables and using that as part of our computation for the next state. So I think that's what you're getting at, right? Like, how do I know what order to determine all these things in? And it's because of like the dependency here, right? I can't find Z first because Z depends on S, right? So I have to find S first. I can't find C in first because C in is just the value of C naught, C out from the last step. Why does C out start high and stay high? It starts high because well, it doesn't really matter. Like, yeah, C out is a function of x1, x2, and C in, right? So at all stages, the value of the output, just you use your truth table here, this truth table, right? That's what the blue bracketing is telling us. So the blue bracketing, like let's just look at this one here, for example, right? It's like 1 plus 1 plus 0. 1, 1, 0. We see that C out is 1. So we have a 1 there. And apparently, for all the other steps, it was also a 1 until the last 3 clocks. So what I'm saying with this like blue bracketing here, the light blue bracketing, is just to say that the C out, carry out, and S are both functions of just A, B, and C. These are A, B, and C, right? X1, X2, and C. Hopefully that clears things up there too. Okay, guys, well, it is 6 o'clock, so that's approximately our time for today. I'll probably not do any more questions, but I will stay around if people have like quick questions on over the chat to talk about. But that's my last kind of full question to do. So the reset didn't apply to the C0. No, the reset doesn't apply. Look at what the reset's attached to, right? The reset. First of all, resets only really applied to like synchronous things, right? So the flip flops are synchronous. Remember the adder. There's no clock attached to the adder, right? It's all just like combinational circuits here that just kind of the information just flows through it, not controlled by any clock. So the reset doesn't do it. There's nothing to reset in an adder. Yeah, the reset doesn't affect the C naught for that reason. The reset also doesn't affect the X1, X2. Well, that's it, I guess. Because X1, X2 are these like switches on a board, right? Switches on a board, you don't have to do that at the moment of the clock. You switch it whatever you want, right? That's also not synchronous, right? These are synchronous. So that's why they have a reset. Again, I guess my point is like, look at what the reset's connected to, right? The reset is connected to those two and not connected to the adder. there are other questions, is it possible to continue choosing effects our own time? Yeah, let's see. I can maybe give one more question. Will you post solutions to the questions you plan on doing for today's session? Yeah, I don't know if I can. I don't know if I can post everything. Like, I don't know. I can't. I mean, I can't post solutions that I haven't written. So I mean, whatever I've written here. I think I can include one more question. Let me just toss in one more question on here for you and see what we can do. A lot of them are like K-map related questions, which are kind of frustrating. So I'll put here's a fine question. I would just remove one of the zeros. Okay, so just ignore that. I'll just, so you can include this as well. It's not particularly hard. It's just a bunch of K-maps. I would remove one of the zeros there. Okay. So I'll post the notes and you can see it there. So, well, that's pretty much it. So I'll again, I'll stop recording on my end.